study the formation of nucleus, the scale for nucleus is actually too small to be studied. So it's actually something that we are not really familiar with. Okay, so if I want to understand the formation of nucleus by explaining how protons and neutrons come together, it might be a bit unfamiliar to you, everything around here. So I'm going to move away from nuclear physics for a while to talk about something that you might be more familiar with. Then afterwards, I'll come back to the study of formation of nucleus. So how am I going to transform our situation here? I'm going to switch to something on the larger scale. So just now we were talking about formation of nucleus, where we bring protons and neutrons together. But now let's talk about something that you have been learning in secondary school, where you try to bring all these H2O particles over here to move it from being a liquid state to a solid state. So we are going to study the transition of H2O from liquid phase to solid phase. So when we undergo transition from being a liquid to a solid, for this case of water over here, we can understand that energy will be released, and we study in secondary school the energy release is called latent heat of fusion, I think. Okay, then opposite is called latent heat of vaporization. And is it? I think this is latent heat of fusion. Yeah, if you are talking about liquid to solid, that's the heat involved over here in order to form ice. Okay, so at the same time, we know that when you are in liquid form, the water molecules are actually more further apart, but when you are in solid form, the water molecules are more closely packed and the arrangement are more orderly in this case. Okay, so in this case, we can say that if we undergo transition from liquid phase to solid phase, the distance between the water molecule decrease, and this causes the energy to be released. Okay, so I want you to associate this decrease in distance, you can associate with the energy being released. So if your process here involve molecules or other stuff, involve molecules going from further apart to be close together, if the distance between the molecules decrease, you should expect that there's energy release, and this is the case for attraction. So now you understand the atomic scale of things, how when we bring things together, energy will be released. We can bring this kind of relationship here back into the nuclear scale. So if you break into the nuclear scale, we know that we want to form a nucleus. So nucleus, if you want to form it, we need to bring protons and neutrons closer to each other. So we're going to go from further apart to close together. So this is something similar to this process in where we go from liquid phase to solid phase. We bring liquid which are more further apart, they are water molecules. We bring it to solid phase where the water molecules are more closer to each other. Similar to a formation of nucleus, we bring protons and neutrons which are further apart, we bring them to be close together. So if this is a process that we are studying, we know that this is an attraction case. So attraction case, just now we discussed that the distance should be decreased. So we can see that protons and neutrons, initially they were further apart, but after the formation of nucleus, those protons and neutrons are brought together to a very, very small distance on the order of 10 to the power of negative 15 meter. So they are now very close together. This is similar to the transition from liquid to solid, and we know that since it releases energy here, right, so we should expect that this process of formation of nucleus should also release energy. So that's the main point I want to convey over here. If we are forming a nucleus, you should expect that energy will be released, and we are going to name this energy here being the binding energy. So for you to bind the protons and neutrons to form a nucleus, there will be an energy being released, and the name of the energy being released is called the binding energy. Okay, so to provide a definition based on our understanding over here, we can define binding energy to be the energy release. Okay, we're talking about energy release to form a nucleus. Okay, so during the formation of nucleus, energy is released. Okay, but how do we form a nucleus? We form a nucleus from completely separated constituents. Completely separated constituents. Constituents means by the ingredients you need to make a nucleus. So in this case, for a nucleus, its constituents are protons and neutrons. So we can substitute this word constituents here as protons and neutrons. So you can say that energy released to form a nucleus from completely separated protons and neutrons. So from completely separated protons and neutrons, we are going to form a nucleus. So once we form a nucleus, there will be energy release, and that energy release we are going to name it as binding energy. And so this is the definition for binding energy. Okay, so this is the discussion of binding energy if we talk about the process of binding the separated constituents to form a nucleus. But we can also talk about binding energy the other way around actually. So instead of forming a nucleus, now we want to break up a nucleus. So we are going to bring all these protons and neutrons which are initially very close to each other, we are going to break them apart so that they are now far away from each other. So we are going to study the opposite process. Previously it was formation of nucleus, now it is now the breaking up of nucleus. So the breaking up of a nucleus, we should expect that it goes from close together to being further apart. So this is breaking up of nucleus. Breaking up of nucleus, you can think of it as to overcome the attraction. Okay, you are trying to overcome the strong force over here to break them apart so that they can move away from each other. So to overcome the attraction, you should think of everything to be the opposite of the case that we have discussed just now. So previously the distance was decreased, but now we can say that the distance between the constituents is increased. Okay, initially the protons and neutrons are close together, but now they are far apart. So just now when we form a nucleus, you should expect the energy to be released, right? So right now, if you are doing the opposite, you are overcoming the attraction, you should expect that if you want to pull things apart, you have to apply some form of energy so that you are able to pull it apart. So in this case, you should expect that energy will be used instead of energy be released. You should think about, let's say you have something being stick together by glue. If you want to break them apart, you yourself have to apply the energy, to use your energy in order to pull it apart, right? So similar idea is applied over here. We want to overcome the attraction, the very strong force that we have over here. If you want to overcome it, you need to use energy in order to break it apart. Okay, so for the breaking of a nucleus, the energy used is identical to the energy that is released when we form a nucleus. So this energy used is also called as the binding energy. So during the formation of nucleus, you release some amount of energy. But if you want to break them apart back to the initial situation, you have to apply some energy to break them apart. And the amount of energy that you need to break them apart is the same as the energy released when you want to form that nucleus. So the process of formation and the process of breaking up a nucleus, the amount of energy used or the amount of energy released is identical. Okay, so we are going to call them by the same name, which is binding energy. Even though we are breaking them apart, but because the amount of energy needed is the same for you to bind them together, so we are going to call it by the same binding energy. So previously the definition was energy released to form a nucleus from completely separated constituents. But now if you are flipping it to talk about the breaking up process, we can say that the definition for binding energy can also be written as the energy used. But now we are breaking up, we are not forming a nucleus, so we can say to break up a nucleus. So what are we breaking up into? We break them into completely separated constituents. Okay, so these two are definitions of binding energy. Both are equally correct. It just depends on from which perspective you want to study the process, whether it's from the formation of nucleus perspective or breaking up a nucleus perspective. But both of these are equally correct. Okay, so to wrap things up, you can say the definition of binding energy is the energy released if you want to form a nucleus, energy released to form nucleus from completely separated constituents. So it means by from being separated into forming one small nucleus, how much energy is released, that's binding energy. Okay, another perspective, it's the energy used to break up a nucleus into completely separated constituents. So the reverse of the formation process. So the amount of energy involved is the same. Okay, so in the next video, we are going to move on to study how do we determine how much is this energy released, how much is this energy used. Okay, we are going to determine the binding energy of the nucleus.